Remember to starting, all the things are being recorded, and copies of the PowerPoints are all available. I can't make anything more available than there is. Scans of all the class notes are available. All that stuff is out there if you need to reference it, okay? That's all on Blackboard. So today we're going to do section 6.6. And this is about inverse trig functions. All right, let me get another. This one looks like it's ready to maybe die on me. Okay. We're going to look at derivatives and integrals involving inverse trig functions. Now, you've all had trigonometry, so somewhere in that trigonometry that you talked about not only trig functions, but the inverse trig functions. We're going to have just a very brief review of that, so it's not going to be a full trigonometry class here. First of all, let me point out this. We're talking about an inverse function here. Let's look at the sine function, sine of x. And basically, if we do a rough graph of the sine of x, it goes through the origin, and then it goes up and down in the right direction, and it also goes up and down in the left direction. Now, remember, if we can take a horizontal line and it passes through the graph at more than one spot, we don't have an inverse. So we have to do something, so this fails the horizontal line test. All right. So therefore, we have to do something with this sine function if we want to look at an inverse. And what we have to do is we restrict its domain to minus pi over 2 to positive pi over 2. All right? And we remember that pi over 2, this is really 90 degrees, minus pi over 2 is minus 90 degrees. Okay, but I'm going to be using the radians here. Okay, the video is not working. That doesn't sound good. Okay, I can get this bigger. Let's do a full screen here. Sorry about that. You know why the video isn't working? Because I forgot to take the cap off of the thing. So it is now hopefully working. That's what I get for getting here at 7:30. I get that. All right. Okay, so hopefully all is good now. All right, so we have to restrict the sine function to minus pi over 2 to pi over 2 in order to get an inverse. So what I want to do here is let's just look at a PowerPoint thing. Let's make this a little bit bigger. So here we're talking about, on the left-hand side, we have the restricted sine function. In other words, it's that graph that I did on the paper, except it's restricted to x from minus pi over 2 to pi over 2. Notice that this passes the horizontal line test. Therefore, it has, oh, thank you. Yes, it would be nice. Boy, it's Friday. Let's make this, let's see, no. PC to O. That's it. Thanks, Susan. All right. Now we've got it on the screen for you guys. What did they say here? Okay. All right. All right. So we have the restricted sine function from just minus pi over 2 to pi over 2. And it goes from negative 1 to positive 1. That's the range of the sine function, or the cosine function also. So because it passes the horizontal line test, we can do an inverse. And what we get then is the inverse sine function. Now remember, with inverses, the range of the one function becomes the domain of the inverse. The domain of the original function becomes the range of the inverse function. So the sine function has a range from minus pi over 2 to pi, the inverse rather, from minus pi over 2 to pi over 2, and its domain is from minus 1 to 1. So the domain and ranges switch places. This has a special name. The inverse sine function is called the arc sine function, A-R-C-S-I-N function. Or we can also just use the inverse notation, sine with a -1 as a superscript, sine inverse. Either one is fine. Okay. Now, so we have that. Let me go over here. Let me go back to, let's see. Let's see if I can get this right. Oh, shoot. What am I doing wrong? I want to get this thing back here. I want to get this thing up like that. It's just not working for me. Yeah, I am. So why isn't it working? Yeah, that's what I'm doing.
There you go.
Okay, thanks. All right. So now let's go on here with this inverse. Okay. Let's go back and recall something here. Recall that with the sine function, say the sine of theta, we find the sine of an angle theta. So we have an angle, we take its sine, and we get a number, all right? i.e., sine of theta is equal to some number. Now, if we're going in reverse for the inverse, that means, therefore, that the sine inverse of that value is equal to theta. We're going the other direction here. So this is what I want to point out then. The inverse sine, its value is really an angle. So the value of sine inverse of x is really an angle. All right. Now, in particular, for the sine inverse, we have this. Sine inverse of x is equal to the angle. So it's equal to an angle. And the angle has got to be between negative pi over 2 and positive pi over 2. And it's the angle between those two values whose sine is equal to the value x. I want to put the big asterisk here by this. This is the way I remember what the sine inverse is. It's the angle between negative pi over 2 and pi over 2, whose sine is equal to x. Does anybody have any questions on that? This is going to be a refresher from trigonometry when you talked about inverse sine functions. Okay. All right. Let's just do a couple of concrete examples with this. So this is right here. This is not calculus. It's back to trigonometry. Evaluate sine inverse of 1/2. So in other words, we want to figure out what sine inverse of 1/2 is. Okay, this is the deal. It is the angle between minus pi over 2 and positive pi over 2, whose sine is equal to the 1/2. All right. Now, in trigonometry, you had a couple of what are called special triangles. One of them was the 30, 60, 90-degree triangle. So this would be 60 degrees, this would be 30 degrees. And the sides of this triangle were 1, square root of 3, and 2. 2 along the hypotenuse. Okay. And of course, we're going to remember that 60 degrees is really pi over what number? Pi over 3. Remember that pi is the same as 180 degrees. One is in radians, the other is in degrees. So 60 degrees is pi over 3, 30 degrees is pi over 6. All right, so let's look at this triangle and figure out which of those angles has a sine equal to 1/2. Sine is opposite over hypotenuse. Any ideas? Pi over 6, the 30-degree angle, its sine is the opposite over the hypotenuse, it's 1/2. So we know that the sine of pi over 6 is equal to 1/2. Pi over 6 is between minus pi over 2 and plus pi over 2. So that is my answer for my sine inverse of 1/2. It's that angle between minus pi over 2 and pi over 2 whose sine is equal to 1/2. All right? Let's do another example with this similar kind of thing. Let's try to figure out the sine inverse of the number 1. Okay, so what does this mean? Well, this is going to be, again, the inverse is an angle between minus pi over 2 and positive pi over 2, whose sine is equal to the number 1. Okay, so what angle between those two values has the sine equal to 1? Pi over 2, 90 degrees, pi over 2. Sine of pi over 2 is equal to 1. So that's my answer, right? I'm sorry, my answer is not 1, it's pi over 2. And that's the angle. Okay. All right. I want to just, I'm going to put this PowerPoint down for a second. Make sure that they're okay. All right. All right. I want to do another type of example here. Again, we haven't gotten to any calculus yet. Let's evaluate the tangent of this angle, arc sine of 1/3. All right. No, not 1. No. Yeah, okay, 1/3. Yeah, that's fine. And let's figure out what this equals. All right, let's remember what this thing is in the parentheses. The arc sine is an angle. So this is the angle between minus pi over 2 and plus pi over 2, whose sine is equal to 1/3. Well, tell you what, I have no idea what angle between minus pi over 2 and pi over 2 that has a sine is equaling 1/3. But what I can do here is draw a picture. Let's call this our angle, right? Let's call this the angle theta. And its sine, the sine of this angle theta, has to be equal to 1/3. So sine is opposite over hypotenuse. So let's put a 1 for the opposite side, that length of 1, and let's put a 3 for the hypotenuse length. Now, what we are asked then is to find the tangent of this angle theta, because that's what we're asked for. Find the tangent of that angle. So the tangent of this angle theta is going to be what? Well, we know tangent is opposite over adjacent. Well, the opposite here is the number 1. How do we figure out what the adjacent side is? Pythagorean theorem. The adjacent side is going to be the square root of 3 squared minus 1 squared, which is going to be what? 9 minus 1, the square root of 8. So our adjacent length is going to be the square root of 8. Okay? All right. And then, of course, if we want to do, we can reduce the square root of 8 as 1 times 2 times the square root of 2, because 8 is equal to 4 times 2, so we can reduce it like that. And that would be our answer then. 1 over 2 square root of 2, like that. Okay, in this case, we had to draw a picture. And frequently, you have to draw a little triangle picture for some of these problems, okay? So everybody figure out this is by drawing this picture, this angle has a sine of 1/3. Drew the picture, I was able to figure out its tangent, okay? All right. Now, let's get to some calculus stuff here. And we're going to figure out the derivative of the sine inverse of x. All right. So for this one, I'm actually going to I'm going to prove what we have as a result. So let's do this. Let y equal that sine inverse of x. All right. And let's take the derivative of both sides. Before we do that, let's rewrite this. If y is the sine inverse of x, then x is equal to the sine of y. All right, we're just reversing it. Or I can write it sine of y is equal to x, like that. Now take the derivative of both sides. Well, the derivative, and we're going to have to use the chain rule. Okay, the derivative of the sine is the cosine. So we're going to start out with the cosine of y, but we have to use the chain rule. We're doing the derivative with respect to x, so we have to multiply by the derivative of the inside function times dy dx, chain rule. And over on the right-hand side, the derivative of x is equal to 1. All right. So let's see what we end up getting here. Let me rewrite this. We have cosine of y, dy dx is equal to 1. So let's divide both sides by the cosine of y. dy dx is equal to 1 over the cosine of y. All right. Well, that's still not a good enough answer because we want our answer to be in terms of x. We want our answer to be in terms of x. Now let's draw another picture here. Oh, I need to move over. All right. Again, we're going to do a picture. Now, from up above, the sine of y is equal to x. So here, y, let's have y be our angle right here in our right triangle, and its sine is equal to x. Well, sine is opposite over hypotenuse, so the length of the opposite would be an x. the length of the hypotenuse would be a 1. Now we want to figure out what the cosine is of this angle. Well, that's adjacent over hypotenuse. So we use the Pythagorean theorem again for that other side, and we get 1 minus x, the square root of 1 minus x squared. So that's the cosine of y is equal to 1 square root of 1 minus x squared. So we can finally fill that in up here, and we get our final answer. The derivative of the sine inverse of x dx is equal to 1 over the square root of 1 minus x squared. Circle that, and I put an asterisk on each side. That's something you need to remember. Yeah?
Where did that x come from?
Okay, I knew that from up here, I knew this y is an angle whose sine has to be x. So I just drew a triangle here, and y is my angle, and sine is opposite over hypotenuse, so I just made this an x, and that a 1. And that gives me x over 1 gives me my sine value. That's it. Yeah. All right. Now, similarly, because you know we're going to be using the chain rule with this. Yeah, Jenna?
How did you get from, because that y equals the inverse sine of x, how did you get from x to x equals sine of x?
Okay, so that's down here. The question is, right here, how did I go from y equals sine inverse of x to x equal the sine of y? Well, with inverses, remember we switch the x's and y's. So here I'm switching the y for an x, the x for a y, and I'm switching from inverse to sine. And that's how I get that. Okay? And just think of the definition here. What's the definition of this? This means the angle y between minus pi over 2 and pi over 2, whose sine is equal to x. All right? Which is exactly what I've written there, that x equals the sine of y. Better? Okay. All right. So since we're going to be using the chain rule with derivatives a lot, I can also write this as using a different letter, the letter u. The derivative of the sine inverse of u with respect to u is equal to 1 over the square root of 1 minus u squared. Okay. And we'll use that with our chain rule. So what I want to do now then is one example of getting the derivative of the inverse sine. Okay. G of x equals sine inverse of x squared. Okay. And we want to find g prime of x, derivative. We're going to have to use the chain rule. Okay. All right. So, basically, g prime of x, first of all, I'm going to, this is equal to our u right here. X squared is equal to our u. I'm just going to use this formula up here to plug in for the first thing that I'm writing, 1 over the square root of 1 minus, now my u is equal to the x squared. So I'm going to do this in 2 steps. It's supposed to be 1 minus u squared, so I'm going to write 1 minus x squared squared. All right, I'm squaring the u. But then I have to finish this off by multiplying by du dx, and of course du dx is going to be 2x. So let's write this a little bit nicer. I have 1 over the square root of 1 minus Now what power of x? X squared squared is equal to what power? 4th. You multiply the exponents. So 1 minus x to the 4th, and then times 2x. And that would be my derivative using the chain rule, okay? Or I could certainly write this, just put the 2x right on top over 1 square root of 1 minus x to the 4th power. All right, same thing. We okay with that first chain rule? All right. Okay, what we're going to move on to next, we're then going to look at the inverse cosine and then the inverse tangent. So we've got 2 more inverses to look at here. This is the inverse sine. These here are those formulas for the inverse sine derivative that you've got to remember. All right, let's go on then to the inverse cosine. Okay. Now, the cosine function goes up and down just like the sine function does. So we have to restrict the domain of the cosine function so that it passes the horizontal line test. So that it passes the horizontal line test. All right. Okay, so this is going to get us back to another PowerPoint here. So let's, Here's the PowerPoint here. All right. There we go. Well, it worked that time, because I did it right, finally. All right, so now we are looking at the cosine function. Now for the cosine function, when it is restricted, its restriction is from x from 0 to pi, which is the 180 degrees. And the range is from -1 to 1. So here's our little segment of the cosine function that is restricted and passes the horizontal line test. So this gives us the inverse cosine function. Again, we switch the range and the domain. So the range of the inverse cosine is from 0 to pi. So it's a different range than the inverse sine function. So this is what it looks like. And again, it's denoted by either arc cos, A-R-C-C-O-S, arc cosine, or the cosine with the -1, the cosine inverse. All right. Either one. Okay, so one of the important things to remember is the range of the cosine inverse function is from 0 to pi. So let's get back here. Let me, let's see, what am I doing here? Okay. All right. I need to move my paper over so that they can see what we're doing. All right. So, inverse cosine. Okay. The cosine function is restricted from 0 to pi, right? And the value of the cosine inverse, or the arc cosine of x, remember it's an angle. The inverse trig functions are angles. It equals the angle between, this time it's between 0 radians and pi radians, 0 to 180 degrees, whose cosine is equal to that x. This is the only way that I can remember this in my head. It's the angle, but this time it's between 0 and pi, whose cosine is equal to the x. Okay. Now, I'm not going to go through like the trig examples like we did before. I'm going to jump right to the derivative here. Derivative of the cosine inverse of x. All right, so I'm not, and it's a similar proof. I'm not going to go through the proof. All right, put an asterisk here. Derivative of the cosine inverse of x with respect to x is equal to, this time it's almost like the sum.
Mr. Smith, can you hear me? Hello? I can hear you, Chris. What up, guys? Mr. Smith? May not mean nothing to y'all. Understand
What?
nothing was... Oh!
Oh, that's all I needed to do. Thank you. Can you hear me now? Okay. Thank you, folks. All right. All right. How did that happen? I wonder, I don't know how would that have just clicked off like that? Did I? Oh, yeah, that's it. Yeah. All right, sorry, folks, but we got it taken care of now. What if the denominator isn't 1? What do you mean by that? What if the denominator isn't 1? Like if it was u over a, what would the derivative be? Are you talking about what would the derivative of sine inverse of u over a be? Okay. All right, let's look at this here. G of x is equal to, yeah, I know. Oh, yeah. Let's get this up here. Okay, G of x is equal to sine inverse of x squared over 5. Is that correct? Is that what you want me to look at? What I just put in there? Okay. All right, so we're going to get the g prime. This is our u function right here. All right, we're going to do the chain rule. So with the sine inverse, it's 1 over the square root of 1 minus u squared. Well, u here, let's do this in 2 steps. Our u here is x squared divided by 5. And that has to be squared. So u squared, 1 minus u squared, times the derivative of x squared over 5 for the chain rule. Okay, so what we have to do is just a little fixing up over here. Let's rewrite again. This is 1 minus. Now when I square x squared, I'm going to get x to the 4th. Sorry if that looks a little small. Over, I'm also having to square the 5 over 25. And that's all under the radical times, what is this derivative? 2x over 5. All right, well, we can fix up this part over here. Let's look at how I can rewrite what's under, yes, Jenna? What's the derivative of x squared over 5? This is 1/5 x squared, right? X squared over 5 is 1/5 x squared. The derivative, I take down the 2, so it's 2 over 5 times x, right? Okay, all right? Yeah. If you just recognize that dividing by 5 is the same thing as multiplying the front of it by 1 over 5. That's it. And then using your power rule. Okay, now here, let's put this all over, under the radical, over a common denominator of 25. So to write the 1, I have to put 25. Because 25 divided by 25 is 1. And then up in the numerator still, I have to put minus x to the 4th power. Okay. And then times 2x over 5. All right, well, let's look at this thing. This 25, it happens to be a perfect square. So I can take out, and this is the tricky part, I can take out this 25 right here. So I'm going to be left with 25 minus x to the 4th power under my radical. I'm going to still, of course, have the 2x divided by 5. But when I take out this 25 here, I'm going to have 1/5 in front. Because I do the square root of 25, which is 5, but this 25 is in the denominator, so I have to keep it here in the denominator. And then there's one other thing I can do with this then. Hey, if I'm dividing by 1/5, that's the same as multiplying by 5. So this is really equal to 5 over the square root of 25 minus x to the 4th power times my 2x over 5. And, well, it just looks like, hey, we got 5s we can cancel out. So let's go on and do that. Should what be negative? The 5, you mean? No, the 5 is going to be a positive. Is that what you meant, Jordan, right?
Yeah, no.
Okay, all right. So what we're left with then, after we cancel out the 5s, is 2x over 25 minus the square root of 25 minus x to the 4th. Does that help? Eureka, does that help? Yes, good. Okay, great. Question on that one. A little bit of algebra involved with that one. All right, let us move on then to the tangent, and then we'll take a little break. So we've done the sine inverse, we've done the cosine inverse. Now we have the inverse tangent. Those are the three that we're going to be focusing on. Okay. So now with tangent, we need to restrict the domain of the tangent function Boy, you know what? Didn't I ask for the tech person like right away, come up right away? And like nobody showed up. That's comforting. If it weren't for you guys, we may not have, we would still be deaf. They would be deaf to me because I probably wouldn't have figured it out. Because I'm over 30. All right? So got to give me a break here on a little bit of this technology. We need to restrict the domain of the tangent function from minus pi over 2 to a positive pi over 2. All right? So let's look at this last PowerPoint slide here. Oops, wrong thing. And got to be careful. Oh, boy. Okay, here it is. All right. Now that's the here, tangent. So the tangent function, we want to restrict its domain from minus pi over 2 to pi over 2. And notice we can't include the endpoints, because at the endpoints, the tangent's either negative infinity or positive infinity. And so this is what the restricted tangent function looks like. Its range is actually any number from plus infinity to minus infinity. Now when we do the inverse tangent function, we basically flip it on its side, and the range then, the domain becomes the range, and the range is minus pi over 2 to pi over 2. So that's important to remember, the minus pi over 2 to pi over 2, and it's called the arctan or the tan inverse. Okay, either one is fine for the inverse. Couple things here I want to point out to you that when we get to L'Hopital's rule, something you're going to probably may need to remember. These two limits right here. These are limits for the tan inverse function. Notice that when x goes to positive infinity, so we're going over here to the right-hand side, If you kept following this graph all the way, this would get closer and closer to that horizontal pi over 2 line. So that means the limit as x approaches infinity of this inverse tangent is pi over 2, asterisk. Then going the other direction, if x is going to negative infinity, the limit as x is going to minus infinity of this tan inverse is negative pi over 2, the other horizontal line. Another thing to remember. So, all right, let me just move, we do this, oops, without cutting off everybody here, let's do this. All right. Oh, yes, let's do this. And I think actually, why don't right now, while I'm getting this settled, why don't we just take a 5-minute break here. Looks like about 3 to 4 minutes after 11, according to that clock, because we've got to be pretty strict, because we missed 6 minutes right away at the front end of class. Okay, so if you want to get up and stretch your legs, please feel free to. Also, if you haven't picked up the homework, the pink sheets for the homework, go on and do that also. Feel free to staple. Don't staple them both together. Is this just the homework assignment? Yeah. Yeah, just staple that together. You share your names on it, of course.
But I didn't know how to do like 1 or 2. That won't be like.
Oh, remember, I think Jenna had asked a question about this. What I'm going to do with this is get my handy number generator app, random generator app on my iPad. And however many problems are on this thing, maybe it's 30 problems or something like that, I'm just going to randomly generate 5 numbers.
I'm going to be sad.
Yeah, it's all by random. Randomly generate 5 numbers, and those are the only 5 that I'm going to even look at. That's fine. I just put them all there. Yeah. So you know, you might be sad, you might be glad. It's one word I could use is a crapshoot. Okay, that's what it is.
Yeah.
Oh, because we haven't gotten to it yet. But it's L, capital L, then not a dash, an apostrophe type thing. And then the word hospital. Oh, with a capital H.
I know. I took French. Okay.
It's also spelled with the O with the something on it,
Yeah.
the caret on it, but the way that they have in the textbook is just HOSPITAL. Huh? Oh, we're typing stuff. What is this going on? Are they typing stuff? Oh, this is what Gung meant to say. Well, we got to move. Let's see. Arcsine. The arcsine is 1 over the square root of. The thing is, with that, you've got, oh, okay, times u prime. Yeah, that'll work out. I think that works out. Check it out. I think that formula's right. Because the a's will cancel out. We have a list for them all. Well, that's good. Okay. So let me ask you this, you Eureka people, and maybe also the Lafayette people. Have I covered anything yet so far in this class that you haven't already seen? That's what I thought.
Yeah, I learned a little bit about markup. We did all a lot of differentiation and inverse.
Oh, well then, that's a brief. The thing is, though, this Calc 2 officially starts at this section. So, oh my gosh. Well, you know, I have to apologize then to you guys because the Calc 2 curriculum starts at these sections, so that's what I have to go with. So it's a good chance for you just to review up on things.
When did they end?
They said they went all the way up through L'Hopital's rule and the donut disc method. And off the top of my head, the donut disc,
The cylinder,
yeah,
That was chapter 5.
yeah. No, L'Hopital's rule is in chapter 6. We're going to be getting to that. Okay. Well, hopefully sometime very soon we will be arriving at stuff that you haven't already had.
I look at
Are you looking forward to that? Good. That's the right answer. All right. Okay, thanks, Jerry. I think everybody's here. Okay. All right. Where were we here? Okay, we're at the inverse tangent here. So, okay, let's just go with the, what tan inverse of x equals. Yeah, I know. Here we go. How's that? Okay, tan inverse of x. Okay, this is equal to an angle. The angle between minus pi over 2 and positive pi over 2, whose tangent is equal to x. All right. Okay. So let us then look at, again, I'm not going to prove this. Well, actually, I'm going to do a trig thing here. Let me just write these limits down again that were on the PowerPoint. The limit as x goes to infinity of the tan inverse of x is equal to the positive pi over 2, and the limit as x goes to negative infinity of the tan inverse of x is the negative pi over 2. So that was on the PowerPoint. Okay, I want to do another kind of, before we get to the derivative of this, let's just do another trig kind of thing here. Let us say we're told to simplify the cosine of the tan inverse of x. All right. There's two ways you can do it, and I'm just going to do it what I consider to be the easy way. Remember, the tan inverse of x is the angle whose tangent is equal to x. And of course, it's the angle between minus pi over 2 to pi over 2, whose tangent is equal to x. So I'm just basically going to do a picture. Now, there's a more formal way that we can do this, but I'm just going to do it this way. Okay, we draw our right triangle, and the tangent of this x, this tan inverse of x, okay, this angle, let's call it the angle theta. Let's put it in our triangle. And its tangent is equal to x. So we know that tangent is the opposite over the adjacent. So we put x over 1 like that. So this one has x units of length, that has 1 unit of length. And what we're asked to find then, what is the cosine of that angle? And again, we're just going to utilize the Pythagorean theorem. This time we're going to figure out the hypotenuse, and it's going to be the square root of 1 plus x squared for our hypotenuse. So we know cosine is adjacent over the hypotenuse, so our cosine of this is going to be 1 over the square root of 1 plus x squared. And that's our answer here for the cosine of this tan inverse. It's 1 over the square root of 1 plus x squared. So here's another example of drawing a picture, right triangle, to arrive at your answer. Okay. I want to do one other example before we get to the derivative here. It's going to be a limit example. Find the limit, LIM, as x approaches 2 from the positive direction of the arctan, or the tan inverse, however you want to call it, of the following expression, 1 over x minus 2. All right, now we've done kind of similar limits like this before. Now let's examine this. As x approaches 2 from the positive side, then x might take away 2 approaches 0 from the positive side. Everybody okay with that? Therefore, which implies 1 over x minus 2, which is the expression that we have, if this is approaching 0 from the positive side, when I divide by it, I'm going to be dividing by smaller and smaller positive numbers, so I'm going to go to infinity, positive infinity. So what we're talking about then is that this expression here is going to be approaching positive infinity. So then, remember our fact here that I wrote on the other page, the tan inverse of x approaches positive infinity as approaches pi over 2 as x approaches positive infinity. So this whole expression here is approaching positive infinity, so therefore this limit is going to be my plus pi over 2. Like that. So the key with these things is to figure out what this inside expression is heading to, and then use your fact that as this expression gets bigger and bigger, the arctangent approaches the pi over 2. Does anybody have a question on that? You got to do a little bit of work here with this. All right? We okay with this? Okay, so the key is to figure out what this inside expression here, what it's heading towards, and then we can figure out what the limit is. Okay. Let's move on then with this. Well, let me ask this question, since I feel the need to ask this question. What if the question had been the limit as x approaches 2 from the other side, the left side, with a minus sign after it, of the tan inverse of 1 over x minus 2. Okay, so we do this. As x approaches 2 from the other side, then taking away 2, x minus 2 approaches 0, approaches 0 from the other side, from the negative side. Therefore, 1 over x minus 2 is going to be heading towards what value? Now we're going to have smaller and smaller negative numbers in the denominator. What's that going to give us as a limit? No, we divide by smaller and smaller numbers, we get bigger and bigger numbers. Well, smaller and smaller, you're meaning negative infinity. Exactly, right. Okay. So this is going to head towards minus infinity this time around. So therefore, this inner expression here is heading to negative infinity. Therefore, this limit is going to be the negative pi over 2. All right, it's going to be a different limit. Okay? All right, let's get in finally then into derivatives of the arctangent derivative. And I'm not going to prove this just for time purposes, but fact, the derivative of the tan inverse of x dx, so this is another thing I'm putting an asterisk by, is equal to 1 over 1 plus x squared. All right. We actually prove it very similarly to how we had done the sine inverse. So again, since we're going to be talking about the chain rule, we know that, say, the derivative of the tan inverse of u with respect to x is going to be, okay, 1 over 1 plus u squared times the derivative of u. Just applying the chain rule to this. All right. So let's do a chain rule example. Let g of x equal to the tan inverse of 5x, and we're going to find the derivative. So this 5x, that's our u. All right. So we start out with 1 over 1 plus 5x in parentheses squared, I'm going to square the u, times the derivative of 5x with respect to x. And then we're going to simplify this. The denominator here is going to be 1 plus, well, 5 squared is 25, x squared is x squared. So that's our denominator. And let's just put it all as one expression here. The derivative of 5x is 5. And that would be our answer there using the chain rule. Okay. All right. Now, all right. I'm going to lay a bunch of stuff on you here that basically really is just going to, most part is just going to be an FYI, because I'm really going to be focusing on the inverse of the cosine, the sine, and the tangent, okay? But the other 3 trigonometric functions also have inverses, okay? So the other 3, so we're talking about the cosecant, the secant, and the cotangent, the other 3. So the cosecant inverse of x is the angle y such that the cosecant of y is equal to x, and this one has the y value has to be and y. We recall this notation, that little kind of look like that funny little small e with a line in the middle. That means is a member of. Is a member of the following set from parentheses 0 to pi over 2, close the bracket, union, parentheses from pi to 3 has pi over 2. This is basically the first quadrant. This is the third quadrant. Okay. Okay, but notice we have 0 and pi are excluded because those would cause the denominator to be 0. All right. We have similar thing for the secant inverse of x. That's going to, again, it's going to be an angle y such that the secant of y is equal to x. And here, the angle y is in the following areas. Y is belonging to, this time it's bracket 0, pi over 2 parentheses. union bracket pi to 3/2 pi parentheses. And this also is the first and third quadrants. We all know what I mean by the quadrants. Quadrant 1, 2, 3, and 4, counterclockwise around. All right. And then finally, we have the cotangent inverse of x. That's the angle y, such that the cotangent of y is equal to the x. And here the y is in the first and second quadrants, and y belongs to 0 to pi, but with parentheses around them, because either of those endpoints causes the denominator to be 0, because cotangent is cosine over sine, and the sine is 0 at 0 and at pi, so we have to exclude those. And so this is the first and second quadrants. All right. What I'm then going to put up here on the paper then are the derivatives of these three formulas here, of these three inverses. Derivatives. And there are differences, obviously, with all of them. The derivative of the cosecant inverse is equal to minus 1 over x. There's an x in front, and here it's x squared minus 1. Remember that the value of a cosecant is bigger than or equal to 1, all right? So therefore, we have to have x squared minus 1 in under the square root. And then the derivative of the secant inverse of x is equal to positive 1 over x times the square root of x squared minus 1. And then finally, the derivative of the cotangent inverse of x, very similar to the tangent inverse derivative, except it has a minus sign in front of it, minus 1 over 1 plus x squared. I'm not putting asterisks by these because in class, I just want FYI, on in-class exams, I'm not going to go here, all right? You got enough to remember, or you will have enough to remember as it is. Okay. I just want to do, before we get on to integrals here, I want to just do just another example with derivatives, another derivative example. And this time we're letting y equal x times the arctangent of the square root of x. And we want to get y prime. Okay. Now, of course, we're going to recognize that we have to use the product rule. We have function number 1 and function number 2. So we have to be aware we're going to use the product rule.